So today in DC electrical circuits, we're looking at lab number 6, parallel DC circuits. And the focus of this exercise is an examination of basic parallel DC circuits with resistors. A key element is Kirchhoff's current law, which states that the sum of the currents entering a node must equal the sum of the currents exiting the node. And we're also going to use the current divider rule. As usual, I've given you some reference sections, and this is in Sham's Outlines Basic Electricity 2nd edition. So we're going to look at the direct current parallel circuits chapter, and we're also going to look at the chapter on Kirchhoff's law, and specifically Kirchhoff's current law. So in chapter 5, we're looking at direct current in parallel circuits. And you can see they give you the formula that the voltage in a parallel circuit is equal to V1 is equal to V2 is equal to V3. So the voltage across all these resistors will be identical. And the total current in a parallel circuit is equal to I1 plus I2 plus I3. They talk about resistance in parallel circuits. And in a parallel circuit, 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus and so on. And they also give you the product over the sum formula. And they give you the division of current in two parallel branches. So I1 is equal to R2 over R1 plus R2 times IT. And you'll notice they have a little typo in here because I2 is equal to R1 over R1 plus R2 times IT. And they give you the formula for power in parallel circuits, so PT is equal to P1 plus P2 plus P3. So in chapter 7 they give us Kirchhoff's laws, and we're interested in Kirchhoff's current law, or KCL. He says the sum of the currents entering a point has to equal the sum of the currents exiting. And in the example, you can see that they've added some currents, and that has to equal the currents exiting the circuit. And they show you the sum of all the currents has to equal 0, where the sum of I, the algebraic sum of all the currents at the common point, is 0. So we have some positive and some negative currents, and they'll all add up to 0. You're given a theory overview about parallel circuits. And you can see the equipment we're going to use today is the adjustable DC power supply, which will be the Agilent power supply, and the digital multimeter, which will be the Mastech multimeter. We have the 1K, the 2.2K, the 3.3K, and the 6.8K ohm resistors, and I've given you pictures of what each of the resistors should look like. So if you're looking at this online, they'll be in color. If not, I've put down the color for each of the bands for you. So we're going to build two circuits today. The first circuit is figure 6.1, and I've gone out on multisim and done a simulation so that we know what kind of numbers we can expect to see when we do our calculations. So figure 6.2 is our second circuit, and you can see it's just a larger version of our first circuit. And I've given you a simulation. This was done in multisim, and I've put all the ammeters in the circuit so that when we do our calculations we can see if we're close or not. So under procedure, step 1, we're going to be using an ohm meter to check the values of the resistors and record those values under equipment. So my 1K is 990 ohms. My 2.2K is 2.153K. My 3.3K is 3.364K. And my 6.8K ohm resistor is 6.8K ohms. So under equipment, I've filled in my model numbers. I haven't put in the serial numbers because they're too hard to find. They're at the bottom of the equipment. And I've put in the values of the resistors that I'm using today. Now you can see on step 2 under procedure, we're going to be doing quite a few things. We're going to use the circuit of figure 6.1. We're going to determine the theoretical voltages at point A, B, and C with respect to ground. We're going to calculate the circuit's total resistance. We're going to record these values in table 6.2. And then we're going to construct the circuit without the power supply. Then we're going to check the resistance reading of the circuit to see if we've built the circuit correctly. So I've filled in my values for figure 6.1, the 8 volts, the 1K, and the 2.2K ohm resistor. Finding the voltages is fairly easy in a parallel circuit because E is equal to VA is equal to VB is equal to VC, so the voltages all the way along are going to be the same. So we're expecting 8 volts at point A, point B, and point C. To find RT, I'm going to take the products over the sum. So that's R1 times R2 over R1 plus R2, and that equals 687.5 ohms. Remember, in a parallel circuit, the total resistance is always going to be smaller than your smallest resistor. So in this case, our smallest resistor is 1K in parallel with the 2.2K, so the expected total resistance is less than 1K, and 687.5 ohms is less than 1K. So you can see in table 6.1, I've recorded my calculated voltages for VA, VB, and VC, all as 8 volts. And in table 6.2, I've recorded my total resistance as 687.5 ohms. So under procedure, step 2, we're now going to construct the circuit without the power supply, set the DMM to read ohms, and apply it to point A and the ground. So we're going to find the total resistance of the circuit, and we're going to record this measured voltage in table 6.2. So I just wanted to show you my circuit here. This is the 1K ohm resistor, and this is the 2.2K ohm resistor. And I just want to remind everybody that the bus lines down the outside, right? So this is where you normally put ICs and components, right? But down the outside, these lines are connected all the way down. And here, these lines are connected all the way up. So the power is coming in and going to my 1K resistor and my 2.2K ohm resistor. Remember, these holes connect all the way down. Then on the other side of the trainer, you can see I have the black wire hooked up to the other side of the 2.2K and the 1K ohm resistor. So these two resistors are in parallel, and this is the way I would set them up on my trainer. You can see I'm going to bring the power in from the white terminal, and the common's going to go to my yellow terminal. So I've connected my two banana leads that go to my digital multimeter, and I'm going to set that to resistance. So you can see I have my digital multimeter set to ohms, and it's reading 0.678 kilo ohms, so that's 678 ohms. So in table 6.2, I record my measured value as 678 ohms. Now you'll notice it's just a little bit lower than the theory, but I want you to keep in mind the measured value of our 1K ohm resistor was 990 ohms, so the resistance in parallel has to be less than 990 ohms. And if you do the calculation using the measured resistor values, you can see it does come out to 678 ohms. I've now replaced the ohm meter with the power supply going to my circuit. Remember, we're going to be using the plus 20 volt terminal, so press in the plus 20 for the meter and use the plus 20 volt adjustment knob to get to 8 volts. So to measure our DC voltages, we're going to put the black lead from the voltmeter into the black lead that comes from common of the power supply and goes to the black lead in the bottom of our resistors. Now the red lead we're going to be using, we're going to place it at point A, and point A is at the back here where it comes in from the power supply, so that's point A. Point B is right here on the top of our 1K ohm resistor, so that's measuring the voltage right there. and point C is on our 2.2 k ohm resistor. So that's putting the probe right here to measure our voltage. So remember, to measure DC volts, we have to rotate the knob 2 positions to the V symbol with the flat line. And my voltage at point A is 8 volts. My voltage at point B on the 1 k ohm resistor is 8 volts. The voltage at point C on the top of the 2.2 k ohm resistor is 8 volts. So you can see in table 6.1, I've recorded my measured voltages as 8.00 volts. So step 3, under the procedure, we're going to apply Ohm's law to determine the expected current through R1 and R2. We're going to record these values in the theory column of table 6.2 and determine and record the total current. So, using Ohm's law, V equals IR, rearranging for I equal to V divided by R, we can see the current through resistor 1, I1, is going to be equal to the 8 volts, which is at point B, divided by 1K, which equals 8 milliamps. I2, which is the current running through resistor 2, is going to be equal to 8 volts divided by 2.2K, which equals 3.636 milliamps. Please note I've gone to 3 decimal places. And IT is going to be equal to the 8 volts and the total resistance. So the total resistance is 687.5 ohms. So that equals 11.636 milliamps. And you can see 8 plus 3.636 equals 11.636 milliamps. So in table 6.2, in the theory column, I've recorded my calculations. So under the procedure, step 4, we're going to set up the DMM to measure DC current, and we need to remember that the current is measured at a single point and requires the meter to be inserted in line. So I just wanted to show you the setup for the meter. We know that all our currents are going to be less than 40 milliamps. Some of them are going to be 11 milliamps, so that's more than 4 milliamps. So if we put it on the 40 milliamp range, we should be able to take all our readings. Remember, the red lead goes in the milliamp hole, the black lead goes in the common hole. So we're going to start by measuring the total current in the circuit. And remember, to measure current in a circuit, we have to break the circuit. So the current is coming in from the power supply. So if I disconnect the red lead from the power supply, I can now connect the red lead of my ammeter to the red lead of the power supply. So that's the red lead of the power supply going to the red lead of the ammeter. Now I can take the black lead of the ammeter and put it into my circuit where the red lead of the power supply went. So the ammeter is reconnecting my circuit for me. So the total current reading on my ammeter is 11.61 milliamps. Okay. Before I can take any more current readings, I have to reconnect my circuit. So I have to disconnect the black lead from the ammeter, and I have to disconnect the red lead from the ammeter, and then I have to put the red lead from the power supply back into my circuit. So these are the 2 leads from my ammeter, and remember, to measure a current through a circuit, I have to break a circuit. So I want to measure the current going through R1, which is a 1 k ohm resistor. So in order to do that, I need to break the path that the current goes through on the 1 k ohm resistor. So you can see I move my resistor lead from the bus line where the power is coming in to an unused bus line down here. So now I can measure between my resistor and the line that came in. So the red lead from my ammeter needs to go where the resistor wire came out. And the easiest place to find where it came out is to trace the red wire back, and it came out from the red lead going to my power supply. So I can put the red lead in where the power supply lead was. The black lead now goes to the resistor to complete the circuit. And the reading on my ammeter is 7.98 milliamps. So now I have to reconnect my circuit. So I take the black lead from the ammeter off, the red lead from the ammeter off, and then I have to reconnect my resistor back where it came from. So there's my circuit back together again. Now I want to measure the current going through R2, which is the 2.2 k ohm resistor, so I have to break this part of the circuit. So you can see I've moved the resistor's wire from the bus line where the power comes in to an unused bus down here. So now I have to measure between where the power came in and the part that used to connect to it. So the ammeter is going to bridge that part of the circuit. So to measure the current flowing through my 2.2 k ohm resistor, you can see I have the black lead from my ammeter going to the resistor, and the red lead I clipped onto my first resistor, which is connected to the power line. And the reading on the ammeter is 3.68 milliamps. And in table 6.2, under measured, I've recorded my readings. Now that I have my measured readings, I can calculate my percent deviation and the power dissipated by each of the resistors. So under procedure, step 5, they want us to cross-check the theoretical results by computing the two resistor currents through the current divider rule, and record these in table 6.3. So using current divider rule, you take the resistor that you don't want over the two resistors times IT. In this case, it's 2.2 k divided by, and I've put brackets around my 1k plus 2.2 k to preserve the order of operations when I put this in my calculator, times 11.636 milliamps, and the total came out to 8 milliamps. The calculation for I2 is equal to R1 over R1 plus R2 times IT. So in this case it's 1k divided by 1k plus 2k, and you'll notice I put it in brackets to preserve the order of operations when I'm typing this into my calculator, times 11.636 milliamps, which was the total we calculated before. And we can see R2 is equal to 3.636 milliamps. And the total of those two does come out to 11.636 milliamps that we'd calculated before. So under procedure, step 6, we're now going to be working on the circuit of figure 6.2 with the 1K, the 2.2K, the 3.3K, and the 6.8K, and the applied voltage is 10 volts. We're going to use Ohm's law to determine the currents through each of the four resistors. Record those in table 6.4. We also have to determine and record the total supplied current and the current IX. Now this current should be equal to the sum of the currents through R3 and R4, and we need to calculate the circuit's total resistance. So looking at the circuit on figure 6.2, I've put in my applied voltage of 10 volts. R1 is 1K, R2 is 2.2K, R3 is 3.3K, and R4 is 6.8K. Now to calculate the current going through each of these, we have to remember that in a parallel circuit, the voltage across all these points will be the same. So the voltage across all of these resistors will be 10 volts. So remembering Ohm's law, V equals IR, I equals V over R. So for I1 is equal to 10 divided by 1 k ohm, what's equal to 10 milliamps. I2 is equal to 10 divided by 2.2 k ohms, which is equal to 4.55 milliamps. I3 is equal to 10 divided by 3.3 k ohms, which is equal to 3.03 milliamps. And finally, I4 is equal to 10 divided by 6.8 k ohms, which equals 1.47 milliamps. Now the current through point X is equal to the current through R3 plus the current through R4. The sum of the currents entering a point has to equal the sum of the currents exiting the point. So the current at Ix is equal to the current through R3 plus the current through R4. So Ix equals I3 plus I4, which is equal to 3.03 milliamps plus 1.47 milliamps. So the current at X is going to be equal to 4.50 milliamps. To find the total resistance, the formula is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Rearranging for RT, it's equal to 1 over 1k plus 1 over 2.2k plus 1 over 3.3k plus 1 over 6.8k, which equals 525.04 ohms. So to enter that on your calculator, you can type in 1 divided by bracket. The first resistor is 1k, so that's 1 exponent 3. And you want 1 over that, so you can press second function. And if you look just above my 2 key, you can see x to the minus 1. So second function 2. So looking at that on my calculator, you can see it's 1 divided by bracket 1e exponent 3, which is 1k to the power of minus 1. Right? That's the 1 over. So now I can say plus 2.2 exponent 3 second function x to the minus 1 plus 3.3 exponent 3 plus 6.8 exponent 3 second function x to the power of minus 1 close bracket equals. And then for your last calculation of IT is equal to ET over RT. In our case it's 10 volts divided by 525.04 ohms, and that will equal 19.05 milliamps. So in table 6.4 you can see I've put in my total current and my total resistance. Do make sure that your currents through I1, I2, and I3 and I4 do add up to the total that you calculated. That way you know you've done all your calculations correctly. So step 7 under the procedure, we're going to construct the circuit without the power supply. So we're going to be using the 1K, the 2.2K, the 3.3K, and the 68K ohm resistor. And we're going to set up the DMM to record ohms and record that in table 6.4. So you can see I have the red power line coming in from my binding post, and it goes down the horizontal bus line. So it goes to the top of all these resistors, my 1K, my 2.2K, my 3.3K, and my 6.8K, and then I have them all joined together in the bottom bus line here, going to my black wire going back to the common on my power supply. So you can see the resistance reading on my DMM is 521 ohms. So on table 6.4, I record my 521 ohms. I compare it to my calculated resistance that was 525 ohms. So since they're very similar, I can conclude that I've wired up my circuit correctly. So under step 7, I'm now going to add the power supply to the circuit, and I'm going to set the DMM to measure DC current, and I want to record the total current of my circuit, and then I'm going to repeat this process for the remaining resistors, and I'm going to record these results in table 6.4. So I've set my power supply up. It's reading 10 volts. It's coming out of the plus 20 volt terminal, goes to the milliamp hole on the digital multimeter, comes out of the common terminal, goes to my circuit, flows through my circuit, comes out the black, and goes back to common. So you can see the total current reading on my ammeter is 18.84 milliamps. So you can see on table 6.4 I've recorded 18.84 milliamps, and in theory I had calculated 19 milliamps. So you can see it's extremely important to calculate these numbers before you do a lab so that you know if you're close to what you expect to see. Now I've put my circuit together without the ammeter in there, so the 20 volt terminal, which is providing the 10 volts, goes into my circuit, and then out of my circuit goes back to common. So to measure the current flowing through a resistor, you have to take the resistor out of the circuit. So I've pulled the resistor leg out of the bus I was using and put it in an unused bus. And then the red lead from the ammeter goes to where I pulled it out from, and the black lead goes to the leg of the resistor. And I'm reading 10.01 milliamps. So to measure the current flowing through resistor number 2, the 2.2 k ohms, I've removed the resistor leg from the bus and put it in an unused hole, and the red lead of the ammeter goes to the hole I pulled it out of, and the black lead of the ammeter clips onto the leg of the resistor, and I'm reading 4.61 milliamps. So to measure the current flowing through resistor number 3, the 3.3 k ohm resistor, I've pulled the resistor leg out of that bus line that it was in, moved it down to an unused hole, plugged in the red lead from my ammeter to the bus line, and the black lead of the ammeter is hooked up to the leg of the 3.3 k ohm resistor. And my reading is 2.95 milliamps. To measure the current flowing through R number 4, which is the 6.8 k ohm resistor, I've removed the resistor leg from the bus line that was bringing in the power, put it to an unused hole, and my ammeter is connected to the bus line, and the black lead is connected to the resistor leg. So I'm reading 1.46 milliamps. So after you take a current reading, it's important to put the circuit back together again, or else you'll change the layout of your circuit. So after each current reading, I put the resistor leg back into that bus line where the power was coming in from the power supply. So you can see in table 6.4, I've entered all my readings, and I only have one left to put in, and that's IX. So under procedure, step 8, we're going to find IX. So we're going to insert the ammeter at point X and record this in table 6.4. So point X on your schematic is in line between points C and D. So resistor 3 and resistor 4 need to be taken out of the circuit. So to separate R3 and R4 from the main power line coming in, I've taken their legs out of the bus that went along the top here and put them in these buses here. So this leg for resistor 3 is in the same group of 5 holes as the leg for resistor number 4. Now the ammeter is coming in and going to where I took those 2 resistors out of. And the black lead for the ammeter is just clipped onto one of those resistor legs. Because both legs are joined together in the same little bus line, it means both legs are connected together. So I can put my alligator clip on R number 4 or R number 3, it doesn't matter, because they're both connected together in that same little bus line. So my current reading is 4.41 milliamps. So in table 6.4, I've recorded 4.41 milliamps. I'm going to leave it up to you to calculate the percent deviation and the power dissipated by each of the resistors. There are 5 questions to this lab, and I'll leave them up to you to answer and hand in with your lab. When you've completed the lab, leave your circuit set up on your trainer so your instructor can verify that it is working correctly, and they can initial your lab to indicate that it is complete.